Good morning, good afternoon, good evening, and welcome to a new lecture on linear algebra. I hope you find a good time, relaxed time to learn this lovely topic. So far, we have studied introduction to linear algebra, then we studied about vectors, matrices, then we learned different ways to solve system of linear equations, and now in today's lecture, we are going to learn inverse of matrix. The inverse of a function at the first is another function that undoes the operation of the original function. In other words, if we apply the original function followed by its inverse, we get back to the original input. And mathematically, we write in this way, right? If inverse or G inverse, something like this, right? And for example, here, if we have v and we input v to this function, then we have fv. If we consider that fv is equal to x and we give x to the g, with g is the inverse, then we come back to v, right? And you need to know that inverse of a function is unique. The inverse of a square matrix A is B, or we can say A inverse. When we multiply A by its inverse, or you can say A multiply A inverse, we have one identity matrix, right? And the inverse of a function we calculate in this way, b equals to 1 by determinant adjacent A, right? In whole today lecture, till the end, I work on this way, right? So we will learn, we will get some examples, we will learn how to find it, which function is invertible, which function is not invertible, we will get, some algorithm and so on. An invertible matrix, also known as non-singular or non-degenerate matrix, is another matrix which is also square, right? For which there exists another matrix like A inverse or B, right? We can say A or A inverse. So we can say A is invertible. It means we can find that inverse for it, and in such a way that you multiply A by its inverse, you get identity matrix. This is the condition that we can say. So we say A is called invertible if there is a B matrix in such a way that A multiply B gives identity matrix, and also B multiply A. You remember that in the case of matrices, we learned that AB is not always equal to BA, but in this case, they must be the same. Result of multiplication of B into A and A to B should give you one identity matrix. So we can say multiplying invertible matrix by its inverse result in an identity matrix, as you can see here. For example, here we want to see whether B is an inverse of A or not, right? So we have this one and we want to check. We don't want to find inverse. Later I will teach you how to find inverse of a matrix. In this case, we have A and we have B. We want to check whether A is inverse of B or not. What we do simple multiplication, right? So this line multiply this line, right? It will give you 1. 1 multiply minus 5 is minus 5, plus 2 by 3 is 6, then it gives you 1. This line multiply this one, right? 1 multiply 2, 2 multiply minus 1, it will give you 0. 3 multiply minus 5, 5 multiply 3, then it will give you 0. 3 multiply 2, 5 multiply minus 1, it gives you 1. So it's an identity matrix. But we have to check. This is A multiply B. We must check B multiply A as well. So it means you bring B this side, A this side, right? In this time, we say this one multiply this one, this one multiply this one, this one multiply this one multiply this. So it is also identity matrix. So then we say B is an inverse of A. Can we say that only square matrices are invertible? Yes. Only square matrices are invertible, and non-square matrix cannot be invertible. So if you see one matrix and the matrix is not n by n, it means the number of rows and number of columns are not the same, then you simply say it is not invertible. In order to find a matrix to have an inverse, it must be square, meaning it has the same rows and columns. This is a fundamental requirement for invertible. Not all square matrices are invertible. So square matrix is a condition to be invertible, but we cannot say that all square matrices are invertible. For example, this is one square matrix. Number of rows, this is n by n, right? It's 2 by 2. So it's a square matrix, but we consider, for example, we have this one, and we suppose that A inverse, so this is A inverse, right? So we consider another square matrix as its inverse. So we multiply these two together and we will see whether we can find an identity matrix or not. So if we do the multiplication, this row by this column, this row by this column, then this row by this column, this row by this column, you will find that these two are 0, right? It means when you have 2 0 here, it means it is not an identity matrix. So we say that this is not invertible, right? This is not invertible. We can use the inverse to solve system of linear equations. For example, we have ax is equal to b. We can say that x is, we want to find x, right? So this is our coefficient. These are variables. And these are known terms, or for example, right-hand side, right? Or noun terms. So in order to find variables, if we can find inverse of coefficient matrix, inverse of this coefficient matrix, then we multiply by b, we can find x values. We know from the first slide that inverse of, in here, we find out the inverse, minus 5, 2, 3, 1. Okay, we find out the inverse for this function. So our coefficient matrix is what? Our coefficient matrix is 1, 2, 3, 5. In the previous slide, we checked that this is the inverse of this one. And we have right-hand side here. We bring right-hand side here. If you multiply these two together, then you will find minus 6 and 5, which is x1 and x2. This method needs high computational resources, and therefore it's not considered as an efficient system. Now, if we have two invertible matrices, can we say that AB is also invertible? It means if we have A as invertible, B as invertible, can we say multiplication of A and B is also invertible? The answer is yes, and here is the proof, right? This is what we want to say, right? So we can say this A B inverse, A multiply B inverse is equal to B inverse A inverse or not. So you can see here, B inverse A inverse multiply AB. So if we keep A inside and bring B outside, this one and this one is identity matrix. B inverse is identity matrix. On the other side, if we do the same, then we can get identity matrix. So it means multiplication of two invertible matrices is invertible. Then we consider a chain of matrices like A, A2, A3, AN. If they are invertible, if you have k matrices, and all of them are square and all are invertible, then the product of them is invertible as well. If matrix A is invertible, how about its transpose? The transpose is also invertible, right? You are well aware that the transpose of a matrix involves flipping its rows and columns. We already know that A inverse multiply A is identity matrix, and it means it is invertible. So now we want to check this one. AT inverse is equal to AT inverse or not. So if we say A inverse multiply AT, this one, right? We get transpose of multiplication of a matrix and its inverse. Still, we can get an identity matrix. And in this case, if we multiply transpose of a matrix by transpose of its inverse, still we can get an identity matrix. The next line, in here, just you can see, is changing the order of multiplication because we want to check always AV is equal to VA. So we can conclude that if a matrix is invertible, its transpose is also invertible. You remember that we already used elementary law operation to solve the system of equations. Those were like interchange, scaling, and adding some value or multiplying or something, or a one row, for example, 2r plus 3r3. Here is the same as changing two row. It means once you multiply one matrix, that any values can be for A, B, C, and D. If you multiply by this matrix, it means you change the rows, right? So this is a kind of kernel, right? You can say this is a kind of kernel. If you multiply this matrix by any matrix in this way, it means you changed the rows, as you can see here. Scaling, we add the constant, right? So if you multiply this matrix by any matrix, it means you multiply k to these components. You can see here. And adding k is the same as the last one. You can see here. And if you multiply this one, it means you say k of this time plus this one. K of this one plus this one, right? This is a row operation using matrix multiplication. So we learned that an elementary matrix, these are called as elementary matrices. Elementary matrices are a specific type of square matrix that represent a single elementary row operation. These operations like swapping rows, scaling a row, and adding multiple of one row to another row. Now, the question is how to find an elementary matrix which helps us to do the row operation. It means we want to find the elementary matrix that change this row by here, right? How to find this elementary matrix. And this is, the elementary matrix. This elementary matrix, how to find this E, which help us that you multiply E by this matrix, you change the rows. So we need to find E, which is a matrix, and if we multiply it by our matrix, it will change the row, same as like the second example. So we would like to find an elementary matrix. To do so, we can try to do some row operations on identity matrix. Let's see one example. In here, this is one identity matrix, right? So if we exchange row 2 and 3, if we change row 2 and 3, we get this matrix. Later, you will see if we use this matrix and multiply by another matrix, it will change the rows. So we are building some blocks, and later we can use these blocks to apply on other matrices to change the rows. Or we can multiply the second row by -4. You can see the second row by -4 and scaling. Or we can add 2 times of row and row 3 to get this one, right? So there are just some row operations that we can do on identity matrix. And these are our elementary matrices. It means whenever you want to change the rows, just multiply your matrix by this one. You want to do a scaling, use this one, just to change this word. You want to do, 2 times a row by another row, use this one, right? These are building blocks. So let's go back to our example. Our goal is to find an elementary matrix. We already find these matrices. Here we go. We have E1, right? If you multiply E1 by A, it will give you this one. What is this? Changing of rows. Changing of rows. Right? This changing of rows. If you do this one, you multiply it by 4. If you use this one, you added 2 times of row 2 by 3, right? These elementary matrices help you to do row operation. You can say the use of elementary matrices for row operation. Later, we use this row operation to find row echelon form, and row echelon form help us to solve system of linear equations. The inverse of an elementary matrix is another elementary matrix that do the reverse operation. So this is inverse of this one, right? And for example, we change row 2 by 3, this one again change back, right? So we already use E1 to exchange row 2 and 3. Performing same row interchange operation gives back to the original identity matrix that we have. If we multiply E1 by E inverse, we can get that identity matrix. The same for the second one here. Elementary matrix E2 multiply the second row by 4, right? So inverse multiply the second row of the result matrix by -1 by 4. Elementary matrix of E3 adds 2 times row 1 to row 3. And this inverse of this one add -2 the third row to the first row, and result get back to the original matrix. What is the difference between row reduced echelon form and elementary matrix? If you remember from the previous lectures, RREF are used for manipulation and analysis of matrices, and later these help us to find solution for complex linear equation. So you remember that RREF is a canonical form that matrix can be transformed into using a sequence of elementary row operations. And you remember that elementary matrix, as we defined it, is a matrix that can be obtained from an identity matrix by performing a single elementary row operation, row swap, scaling, and row addition. So RREF is a specific form that a matrix can be reduced to through a series of operations. RREF is a way of representing a matrix to make its properties and solution more apparent. So elementary matrices also are tools used to perform specific row operations on matrices. They are constructed in such a way that when multiplied with another matrix, they apply a particular row operation, or you can say some kernel. So here, for example, you can see multiplication of elementary matrices by A give you RREF, right? And there exists an invertible matrix P. Inside that, PA is equal to row echelon form, right? So if you find this PA, then you can find the row echelon. So let's see the summary. When A is a square matrix, one side is sufficient. The column of A span R. So we want to check whether A is invertible or not. Different conditions. When we say the column of A span Rn, it means the columns of matrix A form a basis for the entire vector space of Rn. This implies that any vector in Rn can be expressed as a linear combination of column of above matrix A. Then we have for every B in Rn, the system A multiply x equal to B, which is our equation, is consistent. It means that for any vector B in the n-dimensional real vector space Rn, there exists at least one solution x that satisfies the equation. The only solution to Ax, 0, is the 0 vector. The nullity is 0. The nullity of A is 0. The reduced echelon form is identity matrix. There exists an n for this one. For example, for this one here, the rank of A is n. If the rank of a matrix A is n, it means the matrix has a full column rank. In other words, the number of linearly independent columns in A is equal to the number of columns it has, right? Or for example, here in case of the linear independent, if the columns of matrix A are linearly independent, it means that none of the columns in A can be written as a linear combination of others. In the context of functions, we need to understand domain, range, and codomain. The domain of a function refers to set of all possible inputs. What we can input to a function. For example, if you have fx equal to x2, you can enter any number here, r, right? But when we have, for example, fx is equal to root of x, you cannot enter like that. Domain represents the input space. You can say input space. The range, on the other hand, encompasses all possible output values that a function can produce. You can say output space, right? The codomain, however, is related to range. It consists of all potential output values that a function could produce regardless of whether they are actually attained or not. In essence, while the range represents the actual output values, the codomain encompasses all possible output values, even if some are not reached by function. For example, we have some values here. Maybe we have some value here, but this one did not have any corresponding to these, right? So we call this as codomain. This one should be here, right? This one should be here, not here. So it means we have a value here, but this function did not trigger. So 1 and 2 range, but 1, 2, and 3 are codomain. In this scenario, where the domain is represented by Rn, and codomain is Rm, then it's important to note that the range of the function can be at most a subset of Rm. So you can say range is subset of Rm. Functions can be onto, one-to-one, or both onto and one-to-one. A function like f is considered to be one-to-one, or they also call that injective. Injective if for every distinct pair of domain, there exists a unique pair of corresponding elements in here. So 1 by 1, corresponding 1 by 1, not 2, 2, not 2, 2, right? In other words, we can say fx1 equals to fx2 and x1 is equal to x2. If a function is one-to-one, then the codomain is smaller than domain. Then if the codomain is smaller than domain, then it cannot be. It means it should be bigger. If a matrix is short and wide, right? Then it cannot be one-to-one. The inverse is true. If we have something like this, then it can. If a matrix is one-to-one, its columns are independent. And in this case, if a matrix is one-to-one, then we have at most one solution for system of linear equations. A function f is considered to be onto, or also known as surjective, if every element in codomain has at least one pre-image in domain. So it means we have nothing outside that cannot be. In other words, for every B in codomain, there exists at least one A in here in domain. Then we can say fx is equal to B or f is 1. So a function f is onto, then the codomain. If the codomain is larger than domain, then it cannot be onto. If matrix A has one more two there, it cannot be. But the other side is okay. If a matrix is onto, then rank of A is equal to the number of rows. And function is onto, then always have solutions. A function f is onto and one-to-one if the domain and codomain have the same size. The domain and codomain have the same size, and the corresponding matrix A is square. A matrix is invertible if we can find a matrix in such a way that the multiplication of A and B give us an identity matrix. Then we can say B is inverse of A. In this case, matrix A must be one-to-one and onto. An invertible matrix is always square. Let's see one square matrix here, and by n, A is invertible if and only if that reduced row echelon form is identity matrix. So this is our matrix. If we can reduce this one to in, then we say it is invertible. But this one, the row echelon form is not identity. You can say it is not identity, then we say it is not invertible. So summary, if we have a matrix n by n and it is invertible if and only if. So three conditions is onto. The columns of A span R. For every B, I already explained about this one by one. For every B in Rn, the system X is consistent, and also the rank is n. Then come to one-to-one. This case is both one-to-one and R2, and all square matrix. The columns of A are here. The columns of solution is 0 vector. Nullity is 0. This case is for none of them. Here we can see those condition is flowchart for a matrix A is invertible if it is a square matrix. If its RREF, row reduced echelon form, is identity matrix, or A has a product of elementary matrix. So these are the terms that we've learned so far. So if it is square, if row echelon form of our matrix is an identity matrix, if you multiply some elementary matrices to our matrix and you get identity matrix, or the product of elementary matrix to this one, you can see those for changing row operation. Then learn how to find inverse of a general invertible matrix. We just learned some general regulation of inverse matrices. Now it's time to find inverse of a general matrix. If we have a square matrix A and the components are A, B, C, D, right? Then the inverse of this matrix is another square matrix which we show by A inverse, and the components are E, F, G, H. The question is how to find E, F, G, H based on values of A, B, C, D. We already know that the multiplication of a matrix by its inverse gives an identity matrix. It means if we multiply this matrix to this matrix, we get some identity matrix. Based on that, we can conclude that the inverse of a function is 1 divided by the determinant of matrix A, AD minus BC, multiply DA, just we change these two, and we give negative to these two, right? So this is equation to find inverse of a general matrices. And in the case that AD multiply BC is 0, we can conclude that it is not invertible. So let's find an algorithm which helps us always to find inverse of a matrix. If we have a matrix of A which is square, we know that A is invertible if and only if the reduced echelon form of our matrix is identity matrix. To do so, we may need to use some elementary matrices like E1, E2, Ek to do that, right? Which are equal to inverse, and by summation of them, we can get to row echelon form which is equal to our identity matrix. Then the inverse is equal to those elementary matrices, some product of them. Let's see some example. We want to find the inverse of A. This is our matrix A, and we want to find it. And if the result is an identity matrix, we can conclude that this is invertible matrix. So here's our matrix, and you remember from previous lectures that we can simply do row operations, elementary row, simple row operation to do that. Here's my matrix. I want to make this one 0, right? I want to make this one 0. R2 is equal to R2 prime minus 2 multiply this one. So R2 minus 2 of R1. You can get this one, right? Then for this one, I say R3 minus 3 times of R1. So I can make this one 0. So you can see I can make this one 0. Then I want to make this one 0, right? R1 minus 2 R2. This, I can make this one 0, right? For this case, I should make this one 0, right? So I say R3 is equal to R3 plus 2 R2. If I plus 2, this one will be 0. You can see? Now, I want to make this one 1. So very simple. This line multiply minus 1. Then I can get this one, right? And now, the only remaining element is this one. I can say R1 equal to R1 minus 3 R3. Then I can get an identity matrix. And I can conclude that my matrix is invertible. This is the algorithm. We transform A by identity matrix to find into its RREF B. We transform this one to this, and R is the RR form, row echelon form, and B is the matrix, not RR form. Then, if the result of row reduced echelon form is an identity matrix, then we can conclude that A is invertible. In this case, B is inverse of A. Thank you for your attention. Please try and feel free to ask me if you have any questions.